Okay, let's try a little thought experiment. Imagine you're standing on a massive bridge. How much do you really trust the measurements that confirm the strength of those steel cables holding you up? Or what about the parts inside the airplane you're about to fly on? In these high-stakes fields, engineering, manufacturing, science, every single measurement is critical. But what if I told you that no measurement is ever perfect? Let's dive into why that is and what we can do about it.
Well, it's just a fundamental truth of our physical world. Every single measurement, I don't care how precise your instrument is, it always comes with this tiny seed of doubt. A little shift in temperature, a vibration you can't even feel, the physical limits of the tool itself. All these things introduce a tiny amount of uncertainty. So the real question isn't how do we get rid of it, because we can't. The real question is how do we understand it and how do we manage it?
For a long time, we tried to tackle this whole problem of imperfection with two main ideas. We talk about error, the chance you just made a mistake. And we talk about tolerance, basically just setting an acceptable range for that mistake. But it turns out that whole way of thinking has a pretty major flaw.
And here's the problem. The International Guide for Measurement, which folks in the know call the GUM, makes it super clear. A true measurement error is fundamentally unknown and unknowable. I mean, think about it for a second. If you knew the exact error, you would have already corrected for it, right? And then it wouldn't be an error anymore. So chasing after some unknowable mistake, well, it's a dead end.
So, this is the big mental shift we have to make. We've got to move away from trying to fix a mysterious error and start quantifying our uncertainty. See, error is like a ghost. It's the mistake we can't actually see. But uncertainty, that's the shadow the ghost casts. It's the range of doubt that we can see, that we can't measure, and that we can actually account for. It's not about a single fluke measurement. It's a feature of your entire process.
And this leads us to the modern, really powerful definition from the GUM. Uncertainty isn't a mistake. It's a parameter. It's a number that actually describes the spread of possible values. It's really just an honest assessment of what we know and what we don't know. It's our way of saying, look, based on everything we understand, the real value is very likely somewhere inside this range.
Okay, so how do we get that number? We don't just, guess. The world's top measurement experts all got together and created what they call the Guide to the Expression of Uncertainty in Measurement. Everybody just calls it the GUM. And it is the international gold standard for calculating and reporting your uncertainty. Now, the GM framework can look a little intimidating, but it really just boils down to these three logical steps. First, you start by making a list of every possible source of doubt. Everything from the temperature of the room to your tool's calibration. Next, you figure out how much each of those sources contributes to the doubt. And finally, you combine all of them using a bit of statistics to get one single, really useful number.
So how do we evaluate all those sources of doubt? The GUM gives us two toolkits. Type A is what you use when you can repeat a measurement over and over again. You just analyze the data, get your standard deviation, and you're good to go. But Type B is for everything else. It's how you bring in all that other knowledge, like what's on a calibration certificate or a manufacturer's spec sheet, or even your own professional experience.
And this is a fantastic way to picture what a Type B evaluation really looks like. Let's say a manual tells you a value is within plus or minus 4 degrees, but that's all it says. We assume it's just as likely to be anywhere in that range, and that gives us the rectangular shape you see on the left. But what if we have a good reason to think the value is probably closer to the middle? Then we might use a triangular shape, like the one on the right. We're actually creating a model of our knowledge.
So, after you've identified and evaluated all these different sources of doubt, the GUM gives you the math to basically funnel them all down, both your Type A and your Type B stuff, into one final value. And this is called the combined standard uncertainty. It's the single number that tells the whole story of your total doubt.
Okay, so we've got a number. Big deal, right? Well, it's a huge deal because every single measurement we take leads to a decision. Is this a pass or a fail? Do we accept it or reject it? And the minute you have uncertainty, you have risk. The risk of being dead wrong. Let's take a look at how this plays out. Whenever we make one of these pass-fail decisions, there are two ways we can get it catastrophically wrong. Take a look at the top right, a false accept. This is when we say something's good when it's actually bad. Think about a faulty airplane part getting a green light. Yikes. Now look at the bottom left, a false reject. This is when we throw away something that was actually perfectly fine, which just wastes a ton of time and money.
And this quote from our source material just hits the nail on the head. A false accept is dangerous. It can risk lives, lead to massive recalls, and put a company's reputation on the line. A false reject, on the other hand, is just really expensive. It kills your productivity and your profits. Both of these mistakes are driven directly by how well or how poorly you understand your measurement uncertainty.
So, what happens if you just decide to ignore uncertainty altogether? Well, when a measurement lands exactly on that tolerance line, what you have is a coin flip. You literally have a 50% chance of making a dangerous false accept and a 50% chance of making a wasteful false reject. And that is the absolute worst-case scenario.
This is exactly why we quantify uncertainty. It's not just to get a number for a report. It's to manage that risk and move from a 50-50 gamble to a confident, defensible decision. So the question is, how do we actually do that?
The professional solution is to use something called a decision rule. And it's really simple. It's just a formal agreement you make before you even start measuring about how you're going to handle uncertainty. For example, a rule might say, we will only accept this part if the measurement is inside the limit and its uncertainty band doesn't cross over that limit. It completely removes the guesswork.
And a really common way to put a decision rule into practice is with a guard band. It sounds technical, but all you're doing is shrinking your acceptance zone. So instead of passing anything right up to the tolerance limit, you create a smaller, safer zone inside of it. This just makes it a lot harder to accidentally accept a bad part, creating a really important safety buffer.
Another key tool is what's called the test uncertainty ratio, or TUR, and this chart shows you exactly why it matters. The TUR is just the ratio of the part's tolerance to your test's uncertainty. As you can see on the left, with a low TUR of 1:1, your risk of being wrong is huge. But look what happens when your test is at least 4 times more precise than the part you're measuring, a TUR of 4:1. That risk just plummets.
So, the path to making better, more confident decisions is actually pretty clear. First, you have to state your decision rule up front. Second, use guard bands to lower your risk, especially on those high-stakes measurements. Third, always try to use equipment that gives you a TUR of at least 4:1. And finally, you got to vet your suppliers, because your own accuracy is only as good as the labs you depend on.
And this last point is so critical, and people forget it all the time. Your entire measurement capability is built on a chain of other measurements. It's a concept called metrological traceability. You can own the best, most expensive instrument in the world, but if the lab that calibrates it has a high uncertainty, guess what? Their uncertainty just became your uncertainty. Your measurements can never be better than theirs, period.
Which really brings us full circle. Uncertainty isn't a failure. It's not a sign that you did a bad job. As the gum so elegantly puts it, it's the most honest estimate we can make based on what we know right now. It's the very foundation of scientific confidence because it replaces some vague, fuzzy doubt with a quantified, understandable fact.
In the end, the goal is never going to be perfect certainty, because that's impossible. The real goal is to know, with confidence, exactly how uncertain you are, because that's what allows you to manage risk and make really sound decisions. So the final question I'll leave you with is this. In your world, in the decisions you have to make, how much doubt is acceptable?